Hello everyone, JavaMentor.net here. Welcome to the new video. In this video, we will try to solve one more problem by doing this exercise. So I created one array of numbers, and our task is to find in this array where is the number 89, at which position, at which index. So the thing is, we have unsorted array here. So numbers are not sorted in any way. And just to say, we won't write code here. We will just explain principles. Because, code is for your homework, right? What can we do with this array to find where is the number 89? So the only thing we can go from the beginning till the end of the array, and then is this 89? It's not. Okay, go to the next number. Is this 89? No, it's 8. Go to the next number. This is 100. Is that 89? No, it's not. And when we approach that number, then we will return an index. Basically, we can do this with a very simple for loop. And this number can be somewhere nearer the beginning or somewhere nearer at the end. But we are interested about a worst case scenario. So the worst case scenario would be this one. So this number is the last element of the array, right? So if we want to find that element, we need to go through every element of this array. And how many elements this array has? Well, let's say that this array has n elements. That means for this algorithm, with for loop, which is going element by element, a worst case scenario is we need to check n numbers. And in big O notation, so big O notation, we write that in this fashion. O of n. This is not 0, this is O. So worst case scenario, we need to go through n elements for this algorithm to work. This algorithm that goes number by number. Now we solved this problem. Now here we have an array which is sorted. We can also do the same algorithm. Those are just numbers, right? And we can solve this in O of n time complexity. And this O of n, this is a time complexity, which means the bigger our array, it will take more time for our computer to find a solution. It's a time complexity measure. The other measure can be space complexity measure. It means how much memory our computer needs to solve this problem. We will not cover space complexity in the whole playlist, so I just killed all of your hopes, but time complexity in this scenario is very important. So the bigger the array, we need more time to find the solution. Now for our second array, which is assorted numbers, we can do the same algorithm, right? And it will work. And also, if this array grows, our algorithm will be slower. But we can take advantage of this array because it's sorted, and we can have a much better algorithm and much faster algorithm. So what we can do here is we can say, go to the middle of the array and find what is the number in the middle. So let's for a second change this number to 1. It works, this algorithm works for every number, but just for the sake of simplicity in explaining, it will be much easier if this number is 1. So let's take the number which is in the middle of the array. So how many elements we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 13 elements. 13 elements. So let's take 7th elements. That's this one. 6 elements on the left, 6 elements on the right. Take a look at that element. What is that number? 89. Okay, we are looking for number 1. Number 1 is smaller than this in the middle, which means that our number that we are looking for is not in the right side of this array. So we can eliminate whole right side. And now we can treat this array in the same fashion. We go into the middle, which will be number 9. Number 9 is also bigger than number 1. So we can exclude all of those numbers. We are not looking on them. Our number is not there. And in that fashion, we are excluding numbers that we are not looking for much faster. In the array of million numbers, in one iteration, so we are looking at the middle of that array of million elements, in the one iteration we exclude 500,000 numbers in only one iteration. And this algorithm O of n need to go through every single number to find a solution. So obviously this algorithm is much faster, going to middle and then again to middle, and complexity of that algorithm, if you remember from mathematics, is O of logarithm of n. And in our case, if we have an array of million elements with this binary search algorithm, by the way, this excluding half of the array based on the middle number is called binary search. This is the time complexity on 1 million elements. You don't need more than 20 iterations. 20. So logarithm of million is 20. It's much better to check only 20 iterations, 20 numbers than million. So we learned big O notation, which is showing us time complexity, how much time we need to solve some problem. And we learned two algorithms, sequential searching for some element, which is possible if elements are not sorted, or binary search, which we can do if elements are sorted. Also take a note how in our binary search example we are using array, and that's because array is suitable for searching elements based on the position, because if we have an array of million elements, we need to go first on the element with index 500,000, and then based on the result we need to go, let's say, to the element of 250,000 and so on and so on. So many times we will search for elements based on the position. And you remember from one of the previous videos that array is data structure that's suitable for that. And let's say linked list is not a good data structure because we cannot fetch element on certain position that fast. You can try to solve those two things, to write code for those two algorithms. For the first algorithm you need a for loop, and for the second one you need recursion that we just learned about. So I think those might be challenging tasks for you. That's it about binary search and big O notation. In the next video let's learn more about hashing. See you in the next video.